All right. So let's remember where we were. We were sort of about to do something really interesting at the end of last class, and then we ran out of time. So let's remember where we were and then continue on to do that interesting thing. So the thing that was different about what we were doing last class compared to what we've been doing thus far is we wrote down a problem where we don't just care about one objective. We don't just care about regret, which we're, as we start talking about more complicated kinds of regret, we're going to have to come up with a name for what this old-fashioned simple kind was. It's called external regret for reasons understood only by Ricky Bora. And right, like previously, we cared about this one objective, like your overall regret. This is cumulative over all of time. In this setting we talked about last class, we have D objectives. Okay, we're acting sequentially, but every action we take has some cost that accumulates differently in D different objective functions. And the thing we want to do is we want to write down and analyze algorithms that can control all of these losses at the same time. We sort of care about minimizing the maximum loss. And just to sort of keep sight of the various things we've talked about in this unit of the course, this is going to be a general framework that will capture many things, but in particular will capture the kind of swap regret that we studied a couple of lectures ago and we saw was closely related to correlated equilibrium in games. How come? Well, swap regret you can think of as saying, I want to have no regret, not just overall, but also on the subsequence of rounds for which I played action 1, and also on the subsequence of rounds for which I played action 2, so on and so forth. If on each of those subsequences of rounds, I'm playing the best fixed action in hindsight, then I can't gain by playing any function that would try to consistently swap out what I did on the subsequence of rounds for which I played consistently action A for any other action. Okay, so if you've got k actions, you can think of that as sort of really having k-squared objective functions here. Each one, for each pair of actions ij, our sort of objective function corresponding to this pair ij is just keeping track of our regret on those rounds when we played action I to action j. Okay, so maybe just to have a single motivating example in mind, although this is going to be much broader, the kind of framework we're analyzing is, in which we just have these sort of D abstract objective functions and we want to keep them all small. It is expressive enough to, in particular, encode the kinds of swap regret guarantees we saw that would be related to correlated equilibrium. Okay, plus a bunch of other stuff. Okay, so let's sort of remind ourselves of what this framework was, what it was formally, what the key quantities we were talking about were, and then eventually we'll get ourselves up to the point that we can sort of remember what algorithm we're analyzing. So we called this the D-objective optimization game, and it's in a framework that will be, familiar. We've been studying this kind of thing all class. It's a sequential decision-making framework over time. So it takes place against an adversary. So it takes place over a sequence of T rounds. And one thing that's different here is that the adversary has a little bit more freedom, right? Like normally, like when we were talking about no regret, at every round, we select a distribution of our actions. So we go first, then the adversary picks a cost vector, and we continue. Here, the adversary moves, then we move, then the adversary moves. Okay, so what does the adversary do? They get to decide what is the structure of the interaction occurring today. Okay, so if the adversary wants, they can change what our action set is. They can pick our action set. Our action set could be different every day. their action set could be different every day. And how our actions correspond to sort of the increase in loss in each of these D objectives that we care about, that's also something that the adversary can come up with every day. Okay, all of those things can be changing. So we don't, right, we're not, but like this is expressive enough to talk about settings where, because of properties of the environment that maybe we just get to observe as we go along, we don't get to affect, we might not have all of our actions available every day. Okay, so formally, we think about the adversary as selecting an environment which consists of an action set for us, AT, an action set for the adversary, BT, and loss increments. In each of these D objective functions that we care about, you know, basically instructions telling us ahead of time, as a function of the action that we play and the action that the adversary plays, how much the loss will increase or decrease in each of these increments, in each of these coordinates. Okay, so we know what this, the adversary chooses the rules of a game at each round and tells them to us. We know, we don't know what the adversary is going to do, but we know the rules of the game. Okay, and we'll ask for sort of mild regularity conditions here. So the action spaces, they're going to be closed and convex. And so, as usual, if they're not, if they're like, discrete action spaces, say, we will convexify them by allowing the learner and the adversary to randomize in sort of the usual way, right? Like if you don't give me a convex action set, then I'll just say, okay, I'm allowed to pick distributions over actions, and now the set of distributions over actions is convex. Okay, so mild kinds of assumptions of the kind we're used to that we can basically enforce ourselves just by allowing our algorithms to flip coins if necessary. Also, the loss increments will sort of be convex, concave, right? So convex in the action of the minimization player, that's the learner, concave in the action of the maximization player, that's the adversary. Okay, so that's sort of the new aspect, that the environment's changing every day in an adversarial way, but then we go on to interact with the adversary in the way that we're familiar. First, we choose an action. We commit to an action first. Okay, so what actually happens is the learner moves first. Then, seeing our action, the adversary best responds. And when we do that, when we, after we've both picked an action, that specifies a loss increment in each of the D coordinates. Our loss at the end in each of the D coordinates will be the sum of those loss increments. And the thing we are interested in as algorithm designers is making sure that the sum of the loss increments is small relative to something in every single one of the coordinates. We want to control the maximum accumulated loss in each of the coordinates. Okay, so our goal is to somehow control, and we have to talk about with respect to what the benchmark is. Our goal is to somehow control the sum of the loss increments in every single one of the coordinates. So we'd like to come up with theorems that upper bounds the maximum of the accumulated loss. Okay, so that's the environment. Are there that's the setting we're playing. Any questions as we remember this? Same thing as yesterday. Exactly. Like basically last time we wrote down an algorithm and stopped before we could analyze it. And I'm trying to get us to the point where we remember what we're doing so we can write down the algorithm again. Are you looking over here? It's not because of that. It's because the thing we care about controlling is the maximum coordinate. So this max, min, max, all of this takes place after they've chosen the game, defined with respect to the environment they've chosen. Yeah. Yeah, if D was 1, yeah, if D was 1 and the action set was the same, then this is just, like online convex optimization. That's right. So the new thing, the new increment over, like online convex optimization, D is bigger than 1. We have more than one objective. That's the main thing. And then also we allow things like the action sets to change with time. But the main new thing is, is that D is bigger than 1. Like it wouldn't have been too hard to go back and derive these sort of results for online convex optimization where the action set was changing. We just have to be a little bit careful about what our benchmarks were. Like it no longer makes sense to like ask that you do as well as, had you played action 5 every day if you were almost never allowed to play action 5. So you just have, you have to be a little bit more careful about what your benchmark is in the online convex optimization setting if you want to handle changing action spaces, but somehow like in the object we're trying to compete with here, that's naturally folded in already. Okay, so people remember the setting? The setting makes sense? Okay. And so, right, so we want to control, the maximum over all of the coordinates of the accumulated loss in that coordinate. And so like the next question is like, what should our benchmark be? Right, like what's our benchmark? It no longer really makes sense to say things like, best fixed action in hindsight, because again, like the environment is changing every round. You might not even have the same action sets from round to round. What does it mean to say the best fixed action in hindsight? And since the loss increments are changing every time, there's no particular reason to think fixed actions are reasonable, right? So, like basically because everything's changing from every round, it no longer really makes sense to talk about fixed actions. We want to come up with some benchmark that makes sense and that is achievable. That's right. Yeah. And so, okay. And so like, but here we are in lecture, whatever, in this class, like we have the minimax theorem on our mind. So in searching for a benchmark, it is natural to think minimax thoughts. And so in doing so, we look at this and we say, okay, well, once the environment is fixed, the learner moves first. Okay, so the learner is going to sort of, naturally try to get some min-max value, or is naturally going to get some min-max value of this game. Of course, going first is a disadvantage. So better than getting a min-max value of this game would be getting a max-min value of this game. Okay, and so having thought those minimax thoughts, maybe we say, okay, an aspirational benchmark is perhaps what we call the adversary moves first value of the game. How well we could do looking at a single round if the adversary told us their strategy first and we had the advantage of best response. Okay, in a single round, if we wanted to minimize the maximum coordinate and the adversary moves first, how well we could do would be exactly the max-min value of the game. What is that? Well, the adversary goes first. They choose their action to maximize our objective. We turn around and choose our action with knowledge of the adversary's choice to minimize our objective. And what is our objective? Well, it's nothing more than the maximum overall of the coordinates of the loss in that coordinate. Okay, so we think these min-max thoughts to ourselves. We're like, all right, we're playing in the min-max order. Why don't I aspire to get the value I would get if I got to play in the max-min order instead? But then maybe we, like think some more min-max thoughts and we get a little discouraged. We sort of say, okay, well, like the min-max theorem doesn't really apply in this setting because in order for the min-max theorem to apply, we need that the objective function that we care about, it should be convex in the minimization player's strategy and concave in the maximization player's strategy. And although each of these loss increments does satisfy that property, the maximum over them does not. Okay, so we think to ourselves, okay, like the min-max theorem, we know it doesn't apply. Maybe we can try to be clever and come up with a stronger min-max theorem. But then we realize we can't do that either. Like the min-max theorem is just false in this setting. And we gave an example last time where maybe like we gave the d-dimensional example where you pick a distribution, but maybe the two-dimensional example is just as instructive. I pick a number between 0 and 1, you pick a number between 0 and 1, and the loss in the first coordinate is the difference between my number and your number, and the loss in the second coordinate is the difference between your number and my number. Okay, that fits in this framework. The loss increments are linear, so they're definitely convex concave. But the thing I care about is the maximum of those two. Well, what's the maximum of a minus b and b minus a? It's the absolute value difference between a minus b, and it's the absolute value difference between a minus b. Okay, so let's think about a zero-sum game in which I pick a number a between 0 and 1, you pick a number b between 0 and 1, and the payoff is the absolute value difference between those two numbers. Well, if I get to, and I want to minimize it and you want to maximize it. Well, if I get to go second, I get to see your number and go second, I do great. I look at your number and I pick the same thing, okay? And I always guarantee that the difference is 0, which is the minimum possible of an absolute value, right? So if I get to go second, the payoff is 0. The adversary moves first value of this very simple game is 0. But if I get to go first, I'm in trouble. Because if I tell you my number, you can then go and pick something that is farthest from it an absolute value. And the best I can do is pick 1/2. And you pick 1 or 0, right? If I do anything else, you can pick something even farther away. And so the adversary moves first value of this game is 0, but the learner moves first value of the game is 1/2. And more generally, if we make this d-dimensional, it's like 1 minus 1 over d. So it's like sort of a maximal example. Like it can't get worse than this. The payoffs are between 0 and 1 in the first place. Okay? So like, it's not just that the min-max theorem we know doesn't apply. It's that the min-max theorem is not true in this setting when we look at the one-round game, when the thing we care about is the maximum. And so having thought these min-max thoughts, maybe we now start to get sad. Maybe we start to think like we were over-ambitious. The adversary moves first value maybe was an unattainable target because it can, the adversary moves first value just can be much smaller than the learner moves first value. And the environment we're playing in is a learner moves first environment. Okay? But yes. Well, between 0 and 1. So it is a closed convex set. So it satisfies the conditions of the min-max theorem. No. So if it would, right, like, or yeah. What do we have in this example? We have action sets that are closed and convex, so the interval between 0 and 1. Those satisfy the conditions of the min-max theorem. We have two loss functions. The first one is a minus b, the other one is b minus a. Each of them individually is linear, and so satisfies the conditions of the min-max theorem. So if we only cared about one of those objectives, either one of them, the min-max theorem would apply. It is because we care about two of them that the min-max theorem breaks, right? Like if we remove either one of those objectives and leave everything else about the game the same, the min-max theorem applies. So the problem is not the action sets, the fact that they're infinite. The problem is the objective. That is, even though each of the loss functions is convex concave because it's linear, the maximum of the two is the absolute value, which is convex in the minimization player's loss, but is also convex in the maximization player's loss, which it's not supposed to be. It's supposed to be concave. Yeah, so the problem, like mathematically, the problem is that the maximum of a bunch of concave functions is not concave. Okay. Okay, so like we're kind of screwed. At least if we were playing the game only once, right? If we were playing the game only once, this would mean that like if we play first, there's no way we can compete with how well we could do if we played second. Okay, but the reason we have some wiggle room is we're not playing the game only once. Okay, and we're going to try to wiggle out of this using the fact that we're playing the game repeatedly. Okay, like the thing we are trying to control is not, the thing we are trying to control is the maximum accumulated loss over time. In particular, the objective we set out for ourselves is, which we called the AMF regret, is the maximum over all of the accumulated losses of the difference between that accumulated loss and the accumulation of the adversary moves first values of the game. So we know that, okay, and so written another way, it's the maximum over all of the coordinates of the sum of the losses in that coordinate minus the adversary moves first value. Okay, so the thing we know that we cannot compete with because of this example is the adversary moves first value round by round. We cannot compete with the sum of the max over all of the coordinates of the loss of A and B. We can't compete if the max is sort of applied pointwise. But that's not what this is. The max is outside of the sum. And that's why we have some hope, because to compete with this, it's okay, potentially, if every round we have high loss in some coordinate, so long as it is not always the same coordinate. If we could arrange it so that it was always a different coordinate, then on average, the loss could still be small in every coordinate. That's the reason why this problem is not just like impossible on its face. Still not like a priori clear what we should do or whether this kind of thing is achievable, but it's the reason why this counterexample to the min-max theorem does not immediately rule out that we might not still be able to get diminishing adversary moves first regret. Does that make sense? Okay. So how do we do it? We had this algorithm, which was really a reduction from adversary moves first regret to simple regret, to external regret. So this thing gets as a subroutine something like multiplicative weights, an online linear optimization algorithm. Okay? So what we're given is an online linear optimization algorithm. And what do? For each of these rounds, we obtain a distribution over the d coordinates of the optimization game from the algorithm. Okay, so if we're running multiplicative weights, for example, what's multiplicative weights doing? It's maintaining a weight for each of the d experts. The experts here are the coordinates of the learning problem. We get those weights, that distribution. And now we define a zero-sum game. Okay. Remember, at this point, the adversary has told us an environment. So the zero-sum game we define is going to be defined in terms of the objects defining the environment. So Min's actions Those are going to be the learner's actions, AT. Max's actions, those are going to be the learner's, the adversary's actions, BT. And what is the objective function of the game? It is the weighted sum over the D objectives of this D objective optimization game of the loss increment in each of the objectives given the actions chosen by min and max, where when I say a weighted sum, what is it weighted by? It's weighted by the distribution maintained by this online linear optimization oracle. Okay? This is a nice, well-behaved zero-sum game. The action spaces are convex concave as desired. Sorry, the action spaces are convex and closed as desired. The loss increments are each convex concave, and so their weighted sum is as well. This is no longer a multi-objective optimization problem. It's a one-dimensional, zero-sum game that satisfies the concave convex property. So it, satisfies the conditions of the min-max theorem. Okay, and so the min-max theorem is satisfied here. We know how to compute equilibria of games like this. That's what we're going to do. We will compute a minimax strategy A star of this game, and that's what we're going to play. The action that we play at this round of the D objective optimization game is A star, this minimax strategy we computed. Okay, finally, we observe what the adversary did. And our online linear optimization algorithm, multiplicative weights, it's expecting news from us. It told us a distribution. It's expecting to hear back a vector of costs, one for each of its available actions. And so we need to provide that. Well, we'll feed a cost vector to the algorithm where the ith coordinate of the cost vector is just the loss increment in the ith objective function, given what happened. Okay? That's what the algorithm is. Does that make sense? Pretty simple, actually, right? Like we're just, like every day we're optimizing not for the max loss, we're optimizing for some weighted sum of the losses. The nice thing about that is that it satisfies a min-max theorem, though it's the weighted sum. And it's not just any weighted sum, and it's not a fixed weighted sum. It is a dynamically weighted sum where the weights over time are maintained by a no-regret learning algorithm. Okay? Okay, and now, finally, catching up to where we were last time. What is the theorem we want to prove? Well, remember, this is a reduction. Okay, so like we've taken as input like something that is like purportedly an online linear optimization algorithm. So the guarantees of this algorithm that I've just written down, like they can only be as good as the guarantees of the thing it was given. And so the form of the theorem is going to be if the online linear optimization algorithm had a good regret bound in the online linear optimization problem, this sort of easier single objective optimization problem, then this algorithm is going to have a good AMF regret bound in the multi-objective optimization problem. And in fact, the theorem we claimed last time but did not prove was that there was no loss in parameters. It's going to be the same regret bound, in fact. Okay. So the theorem is, let's say that this algorithm has the following regret bound. If I look at the maximum over all of its actions, remember it has one action for each of our loss objectives. If I look at just the regular old regret that this algorithm has to action I, and if you've promised me that is less than R of t, okay, so if this is multiplicative weights, R of t here is like square root of log d times square root of t. Then in any d-objective optimization game, if I look at the AMF regret, okay, so if I look at the maximum over all coordinates of the accumulated loss in that coordinate minus the accumulated adversary moves first values, this will also be bounded by R of t. Okay, so the claim is that because we can solve the regular old experts learning problem with regret square root of log d times t for d experts, we can also solve d-objective problems, d-objective optimization problems with AMF regret bound exactly the same, square root of log the number of objective values times t. Okay, so adding more objectives like is actually pretty cheap. It only costs you like logarithmically. Yeah. External regret is a special case of this. The D objectives are regret detection 1 through D. So if you improved on this, you'd get a better external regret. Yeah, we better prove it then, right? But good. Like, I'm always worried people are going to be like, so what? Like, obviously, good. Too good to be true is like where I like to be. Okay. Questions about the statement of the claim? Yes. Yeah. So let's talk about what, the proof is actually going to be like kind of short and algebraic. So let's just talk about again, like what's going on. Yeah. So like, what is like, how is this a reduction to online linear optimization? Like, what is the role of the online linear optimization algorithm here? The role of the online linear optimization algorithm is to give us a one-dimensional quantity to min-max over that is going to bound the d-dimensional quantity we care about. Why is it going to do that? Well, we're trying to minimize all of these losses. But actually, I didn't rewrite it here. Actually, we want an online linear maximization algorithm. That's sort of important. That the things we're treating as losses in each coordinate, this copy of multiplicative weights, it's treating them as gains. So it's trying to pick coordinates. It's trying to put more weight on coordinates that have high loss. Okay? Now, it's good at that. It's got a regret bound of R of t. And so that means that if I look at say it's multiplicative weights. If I look at the accumulated gain of multiplicative weights over these t rounds, it's going to be nearly as high as the accumulated gain of the best expert in hindsight. That's what a regret bound tells us, a regular old regret bound. But here, the gains of each expert are like the losses in each of our coordinates. And so the accumulated, from multiplicative weights perspective, the accumulated gains of expert 1, that's the aggregate loss in loss function 1. The accumulated gains of expert 2, that's the aggregate loss of loss function 2. And so the fact that multiplicative weights is going to do as well as the best expert in hindsight up to this R of t regret term means that if I look at the accumulated gains of the algorithm of multiplicative weights, that will be nearly as high as the accumulated gains of the maximum over all of the coordinates I of the accumulated loss of objective function I. Okay, so that second thing is the thing we're trying to bound. We're trying to bound the maximum over all of the coordinates of the accumulated gains in that coordinate. And now, the thing that's problematic for us is that it's d-dimensional, and the only fact we know in the world is the min-max theorem, and like it only applies to one-dimensional gains. But now we have an upper bound on the accumulated gains on the maximum of the coordinates in terms of a one-dimensional criterion, which is the accumulated gains of multiplicative weights. Okay, so because the thing we care about is only smaller than the accumulated gains of multiplicative weights, if we can arrange that the accumulated gains of multiplicative weights are small, it must be that the thing we care about, the maximum accumulated loss in any of the coordinates, that's also small. Okay, well, how do we make sure the maximum accumulated gains of multiplicative weights are small? Well, one way to do it is to round by round, make sure the gain of multiplicative weights in that round is small. Okay, what is this utility function? This utility function is exactly the gain of multiplicative weights in that round, right? Because this is the distribution that multiplicative weights puts over each of the experts, and the gain of each expert is this. It's the loss of that expert. So this is the gain of multiplicative weights in that round. And so what the algorithm is doing is it is trying to play so that at every round, the gain of multiplicative weights is small. That is a one-dimensional thing, because multiplicative weights is just going to like have one gain. We're using the regret bound to know that the sum of these quantities upper bounds the maximum over the d objectives. And if we can make sure that this is small in every round, then the sum of these quantities will also be small, and hence this maximum will be small. Yeah. Yeah, yeah. And this, you know, again, like by analogy to like our intuition, that what we're trying to do is force the adversary to make the bad coordinate different at every round. Like multiplicative weights is sort of upweighting those coordinates that historically have been bad. And so when we're min-maxing over this weighted distribution, we're putting more weight on the ones that have historically been bad, sort of forcing the adversary, if they want to make any coordinate large, to make a different one large. Yeah, I don't know. That would be interesting. Like what kind, or you mean like quantitatively stronger regret bounds, or you mean qualitatively different regret bounds? So definitely if you could have quantitatively stronger regret bounds, they would immediately carry over. And in fact, you can do that. So like what we're going to do is plug in the bounds we prove for multiplicative weights, which are like these, you know, root log k t things, which are optimal worst case bounds. But as we sort of alluded to, there are finer grained bounds that are known. Like there are finer grained bounds that depend not on t, but on, you know, the sum of the squares of the losses, things like that. You can plug in those finer grained bounds here and get finer grained bounds here, right? So you know, like anytime fully adaptive bounds, anything that's known for multiplicative weights, you can get it out here as well. In terms of yeah, and sort of in terms of qualitative stuff, I'm like not so sure, because actually like if you go through the different qualitative kinds of regret bounds out there, you know, like adaptive regret, sleeping experts regret, like they fall out of this framework anyway. So I don't know if there's something stronger you could get by like plugging them into this framework. But it's an interesting question. I don't know the answer.
Now, you know, say that you're there are two ones on the other side. So let's say if they like keep switching back and forth, you know, you have to go through, right? Like A minus T is gonna like something obviously if you're only one side, kind of start going towards that side.
Exactly. Like if they're always picking a big number, then I start picking big numbers too, and they can still make the difference high in one of the coordinates by picking small numbers, but that's fine. That's sort of, if they're picking small numbers, then they're sort of, you know, to the coordinate that used to be high, that, you know, they're making that smaller and they're making the other coordinate large. And as you said, you sort of go back and forth balancing it. Okay, so that's the intuition. Oh, yeah. That's right. Yeah, the only parameter here is like the subroutine you plug in. So like this subroutine, of course, might have its own internal parameters, learning rates, whatever. But yeah, you know, come to me with an online linear optimization algorithm that has a regret bound. There are no other parameters here. There are no other choices to make. You plug that in, you get exactly the same regret bound out the other side. Make sense? Okay. Okay, so let's prove the theorem, which will basically just be putting into math the argument that I just told you. Okay, so from the regret bound, of our online linear optimization algorithm, right? Like from the only hypothesis that goes into this theorem, what do we know? Let's just write down what it means to have a regret bound for online linear optimization. What we know is that for every single one of the d coordinates, our regret to that coordinate is small, or regret to having played that coordinate every round is small. Okay, which is just, you know, the sum over all of the rounds of, since we're thinking of this as a maximization problem, not a minimization problem, the difference between the cost in coordinate j, the thing we might supposedly have regret to, and the cost obtained by the algorithm, well, it's a linear optimization problem, so that's just the inner product between PT and CT. Okay, this is like the regret to action j in an online linear maximization problem. And, you know, let's not be coy about what the costs are. We know what the costs are. So just plugging that in, like, what is this? It's the sum over all of the rounds. Well, what's cost j? That's just the loss in coordinate j, given the action played by the learner and the adversary at that round, AT/BT, minus, well, what's the cost of the algorithm? What's this inner product? Minus the sum over all of the round, sorry, the sum over all of the coordinates of PIT, the weight that the online linear optimization algorithm puts on that coordinate, times the cost in that coordinate, which is just the ith loss increment at that round, given the actions played by the learner and the adversary. This is the regret. And what we've been told is that this thing is guaranteed to be less than R of t. That's just the hypothesis of the theorem, that there's this regret bound of R of t instantiated with the actual losses that we've decided in this reduction to feed to the algorithm. You know, or like rearranging, right? Like to get the quantity we care about. Since this is true for all j, it's also true for the maximum j. The maximum j is the thing we care about, right? You're just rearranging this regret expression that gives us that the maximum over all of the coordinates of the accumulated loss in that coordinate, which is just the sum over all of the coordinates, or right, the maximum over all of the coordinates of the sum over all of the time steps of the loss in that coordinate, given the actions that were played. Well, what this tells us is that this thing we care about, the maximum accumulated loss, is at most the sum over all of the time steps of the sum over all of the coordinates of the expected loss of the algorithm, the online linear optimization algorithm, at time step t, which is this weighted sum over the loss increments plus R of t. Right, it's just a rearrangement of the regret bound. The maximum accumulated loss is at most the sum of the per round losses of the online linear optimization algorithm, which, spoiler alert, is the objective function of the game we're solving at each round, plus the regret bound. Okay, so this is sort of the formalization of the statement that the loss of the online linear optimization algorithm upper bounds the thing we care about, up to the regret term. Okay, now so far, this is just telling us, you know, something about an upper bound on the loss as a function of AT and BT. But like, you know, the online linear optimization algorithm is not the thing choosing AT and BT. Like, if we want this to be small, we're going to have to use something about how we're choosing AT. Now, fortunately, the way we're choosing AT is by computing a min-max equilibrium for this zero-sum game. Right, so we know that AT is a minimizer amongst all actions of the learner of the maximum over all actions of the adversary of, well, the utility function in this game, which is the sum over all of the coordinates of the weight that online linear optimization puts on that coordinate times the corresponding loss increment, which is the term that we're summing over here. Now, this is an objective that we can apply the min-max theorem to, because by assumption, each of these loss increments is convex in the learner's actions and concave in the adversary's actions. And this is just a sum. So if right, like convexity and concavity, those are both preserved under two operations, multiplying by a non-negative constant. Okay, like if x squared is convex, so is 1/2 x squared. Well, PIT is a non-negative constant. And also sums, right? If x is concave and x squared is concave, then x squared plus x is also concave. And fortunately, it's also true if they're convex. Okay, so the maximum over these losses, that was not convex concave, that was our problem, but we're no longer dealing with that. The sum over these losses, it is convex concave, and so the min-max theorem applies here. And so what we'd like to do to continue the analysis is figure out what the min-max value of this game is. And because the min-max theorem applies, to figure out what the min-max value of the game is, it is enough to figure out what the max-min value of the game. Okay, so we're interested in the min-max value of the game. But because this satisfies the conditions of the min-max theorem, we know this is equal to the max-min value of the game. Okay, again, as always in these arguments, even though this step is like like notationally very simple, the min and the max get swapped, like this is the step the magic is happening in. Like the min-max theorem is magical. Okay, like everything is easier if you know what's happening before you need to make the prediction. Okay, but what's this thing? This is at most, well, the maximum over the adversary's actions of the minimum over the learner's actions of, what do we have here? It is the non-negatively weighted average of the loss in all of the coordinates. Right, like you play, I play A, you play B, that gives us a loss in each coordinate. And this is taking some weighted average of those losses. Okay, all of the weights are non-negative. Well, a non-negative weighted average of a bunch of numbers is never going to be bigger than the maximum of those numbers, right? The biggest it can be is if they're all equal to the maximum. So this is at most, since this is at some average over the coordinates, this is at most the maximum over the adversary's actions, of the minimum over the learner's actions, of the maximum over the coordinates, of the loss in that coordinate. Just because the the average can never be bigger than the max. But this is by definition the adversary moves first value of the game. Right? That was how we defined the adversary moves first value of the game. Adversary goes first, learner goes second. Look at the maximum coordinate. That's what we just did. Okay. And AT is a min-max strategy. That means that if we play AT, that we get at least, well, the min-max value of the game, which happens to be the max-min value of the game, which happens to be the adversary moves first value of the game. at every round against any strategy of our opponents, right? Like a min-max value, if I play a min-max strategy, it means I obtain the value of the game no matter what my opponent does, in the worst case over my opponent's actions. Yeah. Oh, yeah, these are, sorry. The sum is over the coordinates. Okay. Right, so what do we know? Because AT is a min-max equilibrium strategy for this game, we know that simultaneously, for all strategies that the adversary might play, right, we don't know what they're going to play, but it doesn't matter because the following holds for every single one of them. That the sum over all of the coordinates of the appropriate weighting of the loss increment in that coordinate is at most the adversary moves first value of the game. Right? Like this is the objective function of the game. The algorithm constructively plays a min-max strategy for this game. It's a zero-sum game. The min-max strategy obtains the max-min value, and the max-min value is at most the adversary moves first value of the game. And so our utility, which happens to be the thing we are summing over here, the thing that we are summing over time, is at most the adversary moves first value of the game at that round. And so continuing the derivation over here somewhat non-standardly, this is at most the sum over time. This term we just bounded by the adversary moves first value of the game. So the sum over time of the adversary moves first value of the game plus the regret bound. Okay, which just says the difference between the maximum accumulated loss for all d of our objectives in hindsight and the sum of the adversary moves first values of the game is at most r of t, regret bound. So we proved this theorem. Yeah.
Very, very, very cool. But I disagree with you when you say that the magic appears.
Okay.
Here the first is that okay, the two things have to say the scientific probably.
Okay.
And there's a certain game where the certain scalar
That's right. The sum version of the game, like we're explicitly using that the max upper bounds the sum. So the average version of the game can only be easier than the sum version of the game.
Nearly as far in aggregate as the sum of the max. Sorry, max of the.
That's right. So let's see. So saying that another way, if I said the objective was to minimize the maximum loss coordinate on the one hand, and I said on the other hand, the objective was to minimize some weighted average of the loss coordinates, the thing that I put in the other hand, that's always easier because among other things, like if I can bound the max, I've also bounded any weighted average, but not vice versa. Okay, and also the weighted average version satisfies the properties of the min-max theorem. Now, in general, the weighted average version for any fixed weighting, like it's easier because it's legitimately a substantially weaker statement. But what the existence of no regret algorithms is doing is showing that there is a dynamic way to choose the weightings so that you can upper bound the max by upper bounding this dynamic sequence of average gains. Yeah, I think that's a correct distillation of what's going on here. Cool. Okay, so you can do multi-objective optimization. Other questions? For those who can't hear the commentary because you're on the internet, people are saying that this is incredible. They're weeping, tears are flowing down their faces. Yeah. I hope that you two at home are doing that. Okay. Cool. And maybe it's useful, just to make like the algorithm a little bit more concrete. Right now, it's sort of just, it's written as a reduction, but we've got actual like no regret algorithms we can plug in. Maybe the one that has the one that has the simplest form is exponential weights. We got a really simple closed form expression for exponential weights. Okay, so rather than just appealing to a subroutine, some online linear optimization subroutine that like gives us magic weights, and like interacting with its API, feeding costs back at the end, let's just like write down some concrete weights that'll make this work. The weights that come from the exponential weights algorithm that we derived using the min-max theorem. Okay, so what were those weights? Well, they were the following weights. The weight for each expert I was the exponential of eta over 2 times the sum over all of the previous rounds, rounds 1 through t minus 1, of the gain of expert I in that round, which in this case is just at round t prime, the coordinate I loss increment in the game. Okay, well, that wouldn't be a probability distribution as is because it's not normalized. So we gotta divide by something that makes sure that these quantities sum to 1. We just divide by the weights for all of the coordinates. Okay. Now this is like an algorithm with weights that you can just like compute at home. You don't need to look them up. And now we don't need a hypothesis to this theorem anymore because exponential weights has a regret bound that we proved. And we can just read it off. And what we get is that this concrete algorithm gets AMF regret bounded by at most 4 root t log of D. Yeah. Okay. So maybe I'll, rather than beginning the next section in the remaining 10 minutes, give you back a few minutes, but let's just foreshadow maybe like the kinds of things we're going to start to do. So like what I want to do for the rest, a good chunk of the rest of this class is just like use this neat algorithm we just wrote down to do all sorts of stuff. So the simplest thing we can do with it, that's what we're going to start doing next class, is to give fancier kinds of regret bounds for, online linear optimization, online convex optimization kinds of algorithms, ones that have more than one criteria. Okay, and the kinds of regret bounds we're going to give, I'm going to call them subsequence regret bounds. So you want the same thing as we wanted before. You want to do as well as the best action in hindsight. But rather than defining the best action in hindsight as, on average over the whole sequence, I'll let you define different sequences of days. Maybe the set of all days, the set of all even days, the set of all odd days, the set of all days divisible by 3, the set of all days divisible by 7. Pick your favorite way of chopping up days. And you can promise simultaneously for all of those, subsequences. If I zoom in just on that subsequence, I get rid of all of the other days that aren't in that subsequence, and I pretend that was all that existed, and I look at your performance on that subsequence, then I can say that you did as well as the best expert in hindsight on that subsequence, simultaneously for all of the subsequences. Okay, so by picking interesting subsequences, you can give interesting bounds. For example, I can pick, one thing I can do is I can pick subsequences corresponding to all contiguous intervals of time. This sort of means that you're tracking the best expert over time if the best expert is changing, because you do as well, on any interval of time, you do as well as the best expert on that interval. So if as time goes on, who is the best expert is changing, your algorithm also needs to track the performance of the best expert. That's not something that multiplicative weights does. We can define these subsequences also in terms of external context. Like maybe, you are doing things like predicting how you should allocate some portfolio of stocks. Well, okay, like multiplicative weight sort of says you're going to do as well as like the best single portfolio in hindsight, but you might have relevant signal about the world. Like maybe you know something that happens on Fridays that doesn't happen on other days. You can do as well as the best portfolio on Fridays. Maybe you know something about national holidays. Maybe you know something about the day after earnings reports come out. You can do as well as the best expert in hindsight on the day after earnings reports come out. Okay, simultaneously on however many subsequences you can think of, and what you pay in the regret bound is only log of the number of subsequences, so you can really think of a lot. The subsequences can depend on the actions you take. So I can ask for no regret on the subsequence of days for which I played action 1, and the subsequence of days for which I played action 2, and the subsequence of days for which I played action 3. That's going to give me swap regret. So that's how we're going to get algorithms for computing correlated equilibria. I can do combinations of these things. I can get no swap regret conditional on context, right? No swap regret on days after earnings reports come out. So that'll be the first thing we do with this, just sort of fancier regret bounds. And then we're going to move on and notice that like there's nothing about this setup that restricts us to thinking about regret bounds. And we're going to start to think about other things we might want to do, other desiderata of predictions. And we'll talk about things like calibration and fancy variants thereof that also we will have easy access to now that we know how to optimize more than one objective at a time. Okay. All right, let me give you the last 10 minutes back.